So hello everyone. So my name is Shuhei Matsumoto from Hitachi, and I'm responsible for developing and maintaining as one of core maintainers of SPDK with Jim, Ben, Derek, and Champagne. And today I will talk about past 4 months' effort to use SPDK in the enterprise storage area and to support end-to-end data protection with SPDK. So let's start. This is the content of today's my talk. I will start from some introduction about end-to-end data protection and overview of DIF support in SPDK. And then I will explain some detail of this support in SPDK. And then I will share some data about my initial performance evaluation. And I will close my talk by summary and next steps. So I'm not sure end-to-end data protection is not familiar to everyone. So I want to have some brief introduction about data protection. So data protection refers to data error which occurs during writing, reading, processing, transmitting, or storing, and that causes unintended changes to the original data. And generally, data corruption occurs. The file containing the corrupted data will cause unexpected result when accessed. And the data corruption can occur anywhere, and a lot of reasons to occur. For example, software errors, hardware errors, or firm errors, or human errors. And there are 2 types of data corruption. One is detected data corruption, and another is silent data corruption. And the detected data corruption can be temporary, which we can correct, but silent data corruption have no way to notice that, so silent corruption should be avoided as possible as we can. And to guard data corruption, we have to implement data protection, but individual data protection don't span among different layers and cannot prevent any error which occurs between different layers. So end-to-end data protection is essential to have. And data integrity field, and DIF is the standard one. So SPDK will utilize DIF to guard data corruption. And how data corruption works is in the left side shows at first application creates DIF at data creation, and in the middle, intermediate layers can check when the data transferred on them, and the target devices receive data and DIF and can do final check before storing storage media. And DIF is made of 3 fields, and each size is 8 bytes. The first field is guard tag, and this contains a CLC checksum to detect data error. And the second field is application tag, and this is opaque 16-bit field, and how to use is up to the application. The final one is reference tag, and this tag contains normally the lower 4 bytes of logical block address, and this one is incremented by 1 by each successive blocks. And the reference tag can detect wrong destination of read or write I/O. And especially for NVMe, DIF is very flexible, and there are a lot of variables. So to hide the detail from the application, SPDK introduced DIF library to make easy to use DIF. And I will explain DIF library briefly later. And dealing with data corruption is especially important for storage arrays traditionally. And returning no data is better than returning wrong data. So storage arrays have used DIF extensively, but traditionally, specialized hardware have taken the critical role. And for some hosts that are not aware of DIF, the specialized hardware host bus adapters have inserted or stripped DIF for read or write I/O. And for some hosts that is aware of DIF, for example, enterprise database or enterprise file system, HBAs pass data with DIF for read or write I/O. And if SPDK can support these features without specialized hardware, users can more options. So users can choose which one, hardware or software, depending on their own needs. So I started to work on this feature 4 months ago. And so SPDK 19.04, so it will be released end of this month, will support 2 use cases first. And the first use case is DIF insert and stripped feature in SPDK iSCH target. Why we support this is in traditional storage, the block size 512 plus 8, that is 520 is very popular. So supporting the block size 520 is very anticipated. So I support this case as first. And the second case is DIF pass-through feature in SPDK NB overworks target. And this case is intended to use SPDK-based NB overwork storage as expansion units of existing storage arrays. And so SPDK 90.4 will support only 2 use cases, but we will be able to add another use cases. For example, DIF pass-through feature in SPDK iSCH target, and the DIF insert and strip feature in NB over fabric target storage. So I hope we will support these 2 features in the next, so maybe 90.07. I hope we will do. So this is SPDK stack related with DIF. So at SPDK 18.10, only NVMe driver had supported the feature. Since then, we could have good progress, and the next version will cover the essential feature to support DIF. And this page shows the summary of the update of SPDK 90.4 for DIF feature. And I will mention here about some component I will not mention later. So the first one is Intel ISL. So ISL has been integrated with SPDK recently, and ISL have good CRC computation feature. And by using ISL, we could get 100 times better performance than old loop method. So we use ISL to achieve enough performance in the feature. And the end of components, so SPDK NVMe PAF2 and FRO plugin support all DIF and DIX features in 19.4, and SPDK NB Puff2 has minimal overhead and very usable to verify SPDK's efficiency. And on the other hand, FIO is very flexible and easy to use. So those two tools support all of the features, and so everyone can use these tools to test NVMe SSD more easily about the feature. So from now, I will explain a little detail about DIF support in SPDK. So the first is flexibility is nice to have in SPDK, so we tried to achieve that. If SPDK requires physical contiguity or strict alignment, implementation is very simple, but it's not flexible or extensible. So to solve this issue, DIF library supports any 1-byte alignment and granularity for data payload. So SPDK DIF library can process any type of payload. So we have used two techniques to do that. The first one is when the DIF field is split into multiple fields, we save DIF value, calculated DIF value into temporary area, and to use it later to paste splitted field. And the second technique is when data block is split into multiple pieces, we do piecewise sequential CRC computations by using the interim result as the seed value of the next computation. And so to ensure the quality of DIF library, code review and system tests were not enough. So we added extensive unit tests, and some points we focused on was one is we used fault injection, and which can inject bit flip error into any field and offset. And the second one is we used first a single constant value to fill data blocks, but the single constant value could not find complex error, so we changed the policies and we used cyclic value to fill the test data buffer. And these two techniques were very effective to find a lot of bugs, and so now DIF library is very stable, fortunately. And we SPDK will use NVMe SSD as the backend of iSCSI target and NVMe overclock target first. And we can leave DIF verification to NVMe controller because hardware NVMe controller has that feature, but the NVMe controller doesn't report the location of DIF error. So for last feature, getting detailed error information is critically important. So SPDK finds the location of DIF error instead when the hardware reports DIF error. So the left side explains for read I/O how to do that. So at first, SPDK submits read I/O with enabling DIF checks, and if hardware reports DIF error, submit the same read I/O, but without enabling DIF checks, and to get the old data, including corrupted data. And after that, passing the read date buffer, SPDK finds the corrected date block and storing that information to log, and then return I/O failure to the upper layer. And right-hand side shows write I/O. SPDK submits write I/O with enabling diff checks, and when the hardware reports diff error, fortunately, the write data buffer already have the corrupted data, so without needing to submit I/O again, SPDK simply pass the write data buffer and will be able to find the location of diff error and storing that information to log, and then as same as read I/O, write I/O will return I/O failure to the upper layer. And this is a preparation to subsequent pages. This page shows basic iSCSI read and write sequence. So iSCSI has its own packets called as protocol data unit PDU, and the PDU is made of header and data segment, and the size of data segment is described in the header. And SCSI I/O is made of 3 phases. The first phase is command phase, and then data phase, and then response phase. The left-hand side shows iSCSI read, and for iSCSI read, data is transferred by one or more data in PDUs, and the right-hand side shows iSCSI write sequence. And to reduce the exchange of PDUs, SCSI write command can have data as immediate data, and subsequent data is transferred by one more data out PDUs. So to strip or insert DIF to the data payload, we have to filter out such a PDU first. So next page explains how to filter out and get necessary information from the iSCSI PDUs. So iSCSI target first filters out only PDUs which has data segment, and the filtered PDU, when the filtered PDU is SCSI command PDU has CDB and run ID in itself, but the buffer offset is 0 because SCSI command PDU is the first one. And when the PDU is data in or data out, these PDU don't have CDB or run ID, but they have task transfer tag to identify the SCSI command. So by using that tag, SPDK get the corresponding SCSI command and gets the same information from that PDU. But data in or data PDU have buffer offset in itself, so get it from PDU. And so after that, by passing these 3 information to SCSI layer, SPDK iSCSI target will get diff context. And what to get is at first the start block address to store or read from the storage, and how to get is first decoding SCSI command data and then adding offset, and by that we can get the start block address. And we need another ROTB context information is necessary, and to get that information, to access the backing BDEV of run by matching ID with past run ID. And then after getting diff context, iSCSI target will process actual I/O. So from this page, I will explain actual I/O. And this page shows the key technique to get good performance in SPDK. And this idea is based on the discussion with Jim Harris and Greg Tucker. And Greg Tucker is an expert in Intel ISIL team. And we use special scatter gather list to insert or strip diff, and we avoid extra data copy or any bounce buffer by using that SGL. And how to use SGL is when the TCP/IP stack to read incoming data by passing the special scatter gather list as scatter list. And TCP/IP stack leaves diff space for each block. On the other hand, when the TCP/IP stack writes the outgoing data, TCP/IP stack will use the special scatter gather list as gather list and ignoring diff space and send only data. This technique, we could verify this technique is very effective, and I will share the data later. And this page shows the operational flow when SPDK use the SGL. And first, so as I said before, PDU header has the data size, so we get the data size first, and then based on the size, we allocate data buffer. And incoming data may be split into multiple pieces by any reason, so we have to repeat reading data until reading all data for a single PDU. So we create the loop, and inside the loop, we first create scatter list to leave diff space for each data block, and then passing it to the TCP/IP stack, read the incoming data, and then generate and insert diff into the vacant diff spaces. After compression, we process iSCSI PDU. And this page, so in the last page, I explained incoming data may be split into multiple pieces, and this page shows how to process thus when the incoming data is split. So to process that splitting, iSCSI target adjust scatter list for before every read, and if the newly read starts from the unaligned offset, we steps back to the aligned offset and generate and insert diff to full data block. This may not be enough because we may change this implementation, but I will explain the first implementation here by using simple animation. So we set up SGL to read data block 0 and 1 first, but actual read can get block 0 and only half of block 1. In this case, we generate only diff for block 1. And to do the second read, we prepare SGL to read remaining data to block 1. And when the read can get the remaining all of block 1, we steps back to the aligned offset and generate diff and insert the diff space. This page shows the opposite case, so writes outgoing data with diff strip. This page shows from here, I will share the data of my initial performance evaluation. I created the simple system to evaluate the performance I used 2 Xeon processor servers and connect by a single 10 gig NIC cable. And on the SPDK iSCSI target, I used a single CPU core to evaluate efficiency exactly. And I used the Linux kernel TPC IP stack in this case, but in near future, I want to evaluate the performance based on VPP next. And the third one is I needed to use NVMe SSD which supports scatter list, and so all NVMe SSD don't. Some of NVMe SSDs don't support SGL, and they support only PRP list, but the PRP list didn't work for this feature, so I needed to get more newer SSD, but those SSD worked. And on the other hand, iSCSI initiator side used the Linux kernel-based initiator. And as benchmark, I used FIO and create 8 iSCSI sessions on a single link to saturate the connection. This page shows the initial result of 4 kilobyte random write. So absolute value is not appealing because comparing with NVMe transport, this is very low. But so please ignore the exact absolute value. So, and I will tune or evaluate more in the future. So, but at first, I compared SPDK 19.01 and 19.04 by using the standard format NVMe, but I saw 2% degradation. This degradation was unexpected, but yeah, we could fix this degradation by the great insight by Z.A. Yang. The reason why we got performance degradation was we replaced socket API from receive to read B, but read B's performance was worse than receive even if SGL's number of entry is single one. So I changed the code to use read B only when the number of SGL entries is more than 1. And after that, the performance degradation was gone, and we could get the same performance between 1901 and 1904. And then the third one is the data by when I used NVMe format 512+8 and diff check is enabled. This means that we leave diff space for each data block, but we don't calculate and fill diff value into that space. In this case, the overhead was 9.2%, and the last one is on top of the third one, we enabled the diff check, and this setting added 3.3 overhead, and totally the overhead of diff insert was 12.5%. And this page shows the 4 kilobyte random read, and as same as write, the performance of 1901 and 1904 was same when we don't use any feature of diff. And the third one is we use NBA SSD formatted with 512+8, but we disabled diff check. In this case, the overhead was 7.2%, and on top of the third one, when I enabled diff check, the additional overhead was 5.2%. So total overhead was almost the same, so 12.4%. This is summary and next steps. At first, now SPDK iSCSI target provides diff insert and strip feature without specialized hardware in SPDK 90.04, and the performance evaluation showed that the overhead were a little more than 10%, both for 4 kilobyte random read and write. And the performance comparison was not apples to apple, because we could get good implementation from start, and the absolute value is not so good. So if I measure the performance based on BPP, so the overhead may be changed, but I want to do next step, and I will share the result with you in near future. And some of next steps for this feature is, for the first one is, as I said just now, I want to evaluate performance, and of course, and also I want to evaluate functional feature with vector packet processing. This is the high performance user space TCP/IP stack. And the next item is in SPDK 90.04, we support the BDEM module. Only NVMe BDEM module support diff, but we want to diff support in other BDEM modules like crypto, complex, or RAID. And the next one is it may be helpful to support DIX, separate metadata in BDEM modules for some type of applications. And the final one is to support diff insert and strip feature in NVMe TCP target. And comparing NVMe TCP and iSCSI, NVMe TCP is well considered and simpler than iSCSI target. So hopefully we could support this feature in the next version. So 9007 or 9010 we could get. So that's all from me today. So thank you. So I want to have time to get any question.
I'm curious if you have any input as to why, when you had the calculation disabled, you still saw that 9%.
Why 9% overhead?
Yeah,
So major codes will be creating high, so number of entries of scatter list increased from 1 to 8 when, so we needed to time to create special scatter gather list. So that spent time.
Can I see that first or second slide where you show the
How to do that? Red button? Oh. So, please stop. Second
roadmap?
roadmap. Roadmap. This one? No.
I think back a little more.
This one? Sorry.
Yeah, keep going.
Hi.
Go back.
Keep going back.
Go back.
Right at the beginning. Okay, let's see. This is it.
This one?
Okay, so 1904 will have the NVMe OF?
Yeah.
Okay.
Yeah.
1904.
The second one is 1904, but this requires awareness of DIF to application or hosts. Right. But if you download upstream, you can use now. In that case. Yeah, now. But we will support that feature on NVMe or TCP in near future. But for NVMe RDMA, it may not be so easy because RDMA is direct data placement. So, but
right.
for
Okay.
yeah.
Yeah, what are questions?
Yep, we got one from Darek back here.
So if I wanted to implement protection information in vhost, can I utilize any existing DIF APIs?
vhost, I haven't investigated, but I believe we can use same or similar feature on vhost.
Okay. Do I have to expose some additional APIs from your code, or is the current diff library?
Okay. So, but I don't know any. I don't have enough information, but vhost may require separate metadata between date block and metadata. So, but the current pattern, date pattern is interleaved, so data and metadata. So, if vhost requires separated metadata, we may have to add some feature on top of VDEV or scheduler. So anyway, we have to add a little more features, but of course we can do, but not so immediate, maybe.
Okay, thank you.
Any other questions?
Okay.
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 Thank you, Shuhei.
Okay, thank you.